Now we will apply the Biot-Savart law to some specific examples and see that how we can apply it to find the magnetic field. Of course, as is the case in the electric field of continuous charge distributions, that was possible only when we had a high degree of symmetry. So the first example is this. We have a thin straight wire. So this is thin straight wire, okay, of finite length. So it has a finite length. It's not infinite. We will consider eventually the infinite later probably, and as a limit of this. And it's along the x-axis, and it lies along the x-axis. The current is flowing along the positive x direction, okay? And we want to find the magnitude and the direction of the magnetic field due to this whole current at a point P, which is at a distance A along the y-axis. This is not necessarily in the middle, okay? The y-axis is not necessarily bisecting this into two equal parts. No, not necessarily, arbitrary. Actually, if you look at it here, one end of the wire subtends an angle theta 1 with the y-axis. The other end subtends an angle theta 2. Theta 1 and theta 2 need not be equal, and will generally not be equal. So we want to find what is the magnetic field due to the whole current at this point P, which is a point on the y-axis. So how to proceed? Well, the algorithm, the routine is very similar, or the algorithm or the strategy that we follow is very similar to what we used to do in the case of the finding the electric field of continuous charge distributions. The first thing is find what is dB and write an expression for this dB. Now, dB is, you pick up how to find dB. What do I mean by finding dB? I pick up a ds here, which is some element, okay, which has of length ds, and therefore it is a vector, a small vector ds. Okay, a small vector, I mean the magnitude is small, so infinitesimal vector ds. I pick it here and I write and find the expression dB of this ds at this point P. This is the first thing, using the Biot-Savart law. Now, of course, in the Biot-Savart law, you have in the numerator I ds cross r hat. So this is my r hat here, and this is my ds in this case. Now, since I want to find the field of dB, I will have a vector ds cross r hat. So I want to first let me fix the direction of this dB before I write its magnitude. Well, ds cross r hat, in this case, it will be a vector out of the page again. Why? Because again, if ds is the red, r hat is the blue, okay, then by right-hand rule, my right-hand fingers are pointing along ds and I close towards r hat, so this is coming out of the page, okay? And therefore, the magnetic field due to this ds at this point P is out of the page. What is the magnitude of this? So it's pointing, according to this geometry, it's pointing along k hat vector. Because you know, this is I hat, this is j hat, k hat is out of the page. So it's out of k hat. Now, ds cross r, what's the magnitude of this vector? It is modulus ds multiplied by 1, which is modulus r hat, multiplied by sine this angle, the angle between ds and r hat. But for reasons that will become clear, I will express this in terms of theta. So sine this angle is equal to, which is, what is this angle? This angle, pi over 2 minus theta, this angle here. So sine this angle is cosine theta, okay? So I write the Biot-Savart law, the dB for the magnetic field of this ds becomes mu 0 I over 4 pi. This expression here, which is ds cross r, it is just dx. I replace ds with dx because the magnitude of ds is just dx, because this is along an infinitesimal element along the x-axis. So it is dx cosine theta, because y cosine theta, it came again from here. It is sine this angle, but this angle is pi over 2 minus theta, and so it becomes cosine theta, and the r square comes from the Biot-Savart law, and it is along k hat. So this is dB for this ds. Now I note, so this is the first thing. You write down your expression for dB, okay, and find what is its magnitude and what's its direction. First, I note here that all ds's which cover the whole length of the wire will contribute at this point P, because this is the point where I want to find the magnetic field, at this point P. All these dBs here, the ds's here, contribute a dB, each one of them contributes a dB, which is also in the same direction. Okay, they all contribute a dB which is out of the page. So you can just, add these up. You can just check this. Take any ds, write the corresponding r hat, show the corresponding r hat, use the right hand rule, you will find that it is out of the page. And so this is important. So now on, you know what is the direction of the magnetic field due to all these ds's. It's all along the k hat, so it's all out of the page. So I don't need to bother anymore about the direction. Okay, so I will just handle the magnitude. Now, this is something that first I have to keep in mind. The second thing, I try, as I used to do in the case of the electric field, I try to enumerate or substitute for the expressions in the formula, like r, for example, or so, using the geometry that I'm giving. For example, r in this case, which is this distance, which comes from the Biot-Savart law, r expression. What is this r expression in this case? It is a over cosine theta, because cosine theta is equal a over r, so r is equal a over cosine theta. I define this. I also know that x is equal minus a tangent theta, because tangent theta is equal x over a. Okay, so and this is negative because x here is a negative quantity, as you can see. The x is the coordinate of ds, and here it is negative. And so dx is given by this expression. And so if you substitute these for dx, because x doesn't appear, and substitute for r in this expression, then this is the expression that you get for dB magnitude. I don't write dB vector anymore because I know what's the direction. So it is this, minus mu naught I over 4 pi a cosine theta d theta. So this is your dB. And if you look at it here, a is constant. It is just the vertical, it's just the y coordinate of the point P, which is fixed. Mu naught I and 4 pi everything. So the only variable here is cosine theta. Okay, so the only quantity that changes is actually cosine theta in this case. And so by enumerating these, enumerating the quantities in the formula from quantities from coming from the geometry of the figure, I got this. And of course, this immediately tells me what is the integration variable. Okay, it seems the integration variable is theta. And I check that this makes sense when I integrate over theta, because when you are summing all the ds's, this theta actually changes. Each ds has its own theta. So when you are summing over all the ds's to find the field, to add up the dBs of each of these ds's, you are actually you are actually integrating over theta. And so what remains is, this is just what I have said, which remains is just the integration of this expression, and this is just integration over theta, cosine theta d theta, and goes from theta 1 to theta 2. Okay, theta 1 and theta 2 are, the angles subtended by the two ends, and this is the expression that we get for the magnetic field of a straight wire that lies along the x-axis, and this where P here, the point P, which is at a distance a vertically above that wire. Okay, now this is quite a general relation, actually, quite a general relation. What you need to do is just to draw the line, show where is P, draw this line A, find this distance, and find what is theta 1 and theta 2, plug them into this formula, and you will find it. Okay. So this gives you the relation for any straight wire, okay, at a given distance A from that wire. And as you can see, the meaning of this immediately, it suggests that A here, it is just depends on the distance, okay? And we will come to this point later. Now, even if I started from this relation suggests that if P here was not just along the y-axis, but was along the z-axis, for example, I will get a different direction for the field, but I will get the same magnitude if A were the same. Okay, I mean, if this were your current and you want to find the magnetic field somewhere else here, for example, so this is your current, and I want to find the magnetic field at a given A here. Okay, so in this case, this was my expression, and you have theta 1 and theta 2. Even if it's here, if that point were here, okay, at a given A, you will get the same expression. So it depends upon this distance. Even here, it's the same. The direction of the field will be different, might be different, because it's found by the right-hand rule, but it will have the same direction. So actually, what does this suggest? If you consider a circle, if you are on a circle, or if you are on a distance A of this point here, in a circle, and you consider a circle centered at the wire, which has radius A, the magnitude of the magnetic field, not the direction, the magnitude of the magnetic field at all points on this circle are the same. Okay, this will become evident when we do this. Now, it's natural to consider the limits, and in this case, what is the limit? The limit of an infinite line. In other words, when this goes to minus infinity and this goes to infinity. Now, evidently from here, when this goes to minus infinity, then this angle theta actually goes to pi over 2, and this angle here goes to pi over 2. Okay? More precisely, theta 1, note that the angle here is taken with the y-axis. Theta 1 goes to pi over 2, and theta 2 goes to minus pi over 2. So in this case, the limit of an infinitely long wire corresponds to substituting for sine theta 1 minus sine theta 2, sine pi over 2 minus sine minus pi over 2. Well, sine minus pi over 2 is minus 1, and so this result gives me 1, and you get this very simple and elegant expression for the magnetic field of infinitely long wire at a distance A from the wire, any point on the wire. So I'm talking about a long wire. This is the wire. Just take a distance A here, okay, at any point, okay, because the wire is infinite, okay. So just go to a distance A here, regardless of where is this A, okay, it might be here, might be here, might be here, might be here, wherever it is. As far as this A is constant, the magnitude of the magnetic field in this case is the same at all points on that are at a distance A from the wire. When I say distance A, I mean vertical distance. This is the definition of a distance, okay? So if you are at a given distance of the wire, move along the wire. At all points, you will feel the same magnitude of the magnetic field. Rotate. Go at any point. This point A here, it is here, it is here, it is here. As long as the distance is still A from the wire, the magnetic field, the magnitude of the magnetic field will always be the same. This is what does this mean. So for a long, infinitely long wire, this is the expression. Of course, as was the case with electric fields, there is nothing really infinite in physics. When we say infinite here, this is actually approximately equal to the magnetic field of a finite wire, given that this wire that I am looking at the magnetic field at a distances A from the wire that are much smaller than its length, and I am away from the edges. I am near the center. In that case, the magnetic field of this wire is approximately equal to the magnetic field of an infinite wire. So the infinite wire is a theoretical model. okay, that we use theoretically. But the magnetic field that we get here for this theoretical model applies well to a good approximation to a real wire, given that this wire is long comparison to the distance that about at which we are trying to find the magnetic field, and that we are away from the edges. We are near its center. Okay, so that's what it is.